Hello everyone, myself Dr. Kadambari Agrawal, Associate Professor in Department of Computer Science and Engineering, ABES Engineering College. And today I would like to discuss the relations in discrete mathematics. And relations plays an important role in the basis of discrete mathematics. First of all, I will like to define the relation. Suppose we are having two set A and B. Then the relation from set A to B is a subset of Cartesian product of A cross B. Suppose we have to take the Cartesian product of A and B first, then the relation will be a subset or it may be the proper subset of Cartesian product of A and B. We use the notation A R B, or we can denote the relation by A comma B related to R. Then in that case we say A related to B. If A is not related to B, then the notation is A comma B not related to R. If R is a relation from set A to itself, then we say that R is a relation on A. In other words, a relation on the set A is a subset of Cartesian product of A with itself. For example, suppose we are having a set A and it is having the elements 1, 2, 3, 4. Then the Cartesian product of A cross A and the relation is defined. Suppose we are defining the relation with A comma B such that A is less than B. Then in that case, we will consider the order pair in which A is less than B, like 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. In all these pair, you can see the A value is less than B value. Now, the next important concept related to relation is domain and range of a relation. Let R be the relation from A to B. Then we have the domain and range. In very layman kind of thing, domain is right hand side and range is, domain is left hand side and range is right hand side. For example, let A is equals to 2, 3, 4 and B is 3, 4, 5. Then, suppose I am asking you to solve the list of element of each relation R defined below and find the domain and range of R such that in part A, suppose we have to find A related to B. If A is less than B, in B, we have to find A is related to B if and only if both A and B are odd numbers. In C part, suppose we want to calculate A related to B if and only if A divides B. Now, the solution for this particular question is we have the set A, it is having the element 2, 3, 4, and we are having the set B, we are having the element 3, 4, 5. In first, as you can see, the first was that A is related to B if A is less than B. That means we have to consider all the elements in which A is less than B. All the order pair will be 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. So this is a relation which was defined as a is less than B. And now we can define the range in it as 2, 3, 4, all the left hand side element. And it should be unique. Repeated will not be considered. Range is a right hand side, 3, 4, and 5. In the second, we are finding the A is related to B if and only if both A and B are odd number. So first of all, we will find the pairs 3 and 3, 3 and 5 will come in this. Range will be 3 and the range will be 3 and 5 and domain will be 3. And in the C part, we are defining the relation like A is related to B if and only if A divides B. In this, following order pair will come. That is 2, 4, 3, 3 and 4, 4. And we can find the domain as 2 and 4 and range is that is a 4, 3 and 4 is coming again, so we will not consider it. Now, the formula for number of relations. Let the number of elements of set A and B are M and N respectively. Then the total number of elements in Cartesian product of A cross B will be M cross N. Therefore, the number of elements in the power set of A cross B will be 2 raised to the power Mn. Hence, the number of relations will be 2 raised to the power Mn. For example, if we are having a set A, which contains 2 elements, 1 and 3, and B contains 2, 3, 4. Then the total number of relations from A to will be 2 raised to the power 2 cross 3. Because in set A, there are 2 elements. In set B, there are 3 elements. So it will be 2 raised to the power 6 is equals to 64. Now it's very important to define the types of relation. The first is the inverse relation. Let R be a relation from A to B. The inverse of the relation will be denoted by R inverse, and it will be simply defined as by changing the order pair. R inverse, suppose we are having the B comma A, then it will become A comma B. Example, A is equals to 1 to 3 and B is a set having elements X, comma Y, comma Z. Suppose we are defining the relation from A to B. If we are writing the order pair as 1Y, 1Z, 3Y, if I am saying we have to find the inverse of this relation, then the inverse of this relation will be Y comma 1, Z comma 1, Y comma 3. And this is an important identity term, that is our inverse of inverse is the original relation. If R is a relation on A, then R inverse is also a relation on A. Now, types of relation is continuing with other examples also. Suppose we are having a set A having elements 2, 3 and 5 and set B having elements 6 at 8 and 10. Then R is a relation from A to B such that X and Y belongs to R if and only if X divides by Y. This is how we are defining the relation in this numerical, that is if X divides Y. That means we'll consider the elements only in which X divides Y. Then we have to find the R and R inverse and we have to find the domain and range. So first of all, we will find the relation. Relation is defined as X divides Y. So it will be 2, 6, 2, 8, 2, 10, 3, 6, 5, 10. In all this, we can find that X divides Y. Now we have to find the inverse. The inverse we will change simply the order pair of the relation. That is a 2, 6 will become 6, 2, 2, 8 will become 8, 2 and so on. Domain, as we know very well, it is a left hand part and the range, it is a right hand part. So domain will be 2, 3, 5, 2, 3 and 5 and range will be 6, 8 and 10. Similarly, for the inverse relation, we can find the domain and range. Now, this is the types of relation. Continuing, identity relation. The identity relation on set A is defined as IA such that X is related to itself. For example, let A is a set 1, 2, 3, 4. Then IA is 1 is related to itself, 2, 2, 3, 3 and 4, 4. Void relation. A relation on set A is called a void relation if R is a null set. For example, universal relation. A relation R on set A is called universal relation if R is equals to Cartesian product of A cross A. For example, let A is a set 1, 2, 3. Then the universal relation on A is we will find the Cartesian product of A with itself and all the elements will come in it and it will become the universal relation. Reflexive relation. A relation R on a set A is reflexive if A is related to itself. A reflexive relation means an element is related to itself for all belongs to set A. For example, if the relation is equal to 1, 1, 2, 2, 2, 3, 3, 3 on set A is a reflexive relation because in this particular relation, all the elements related to itself are coming like 1, 1, 2, 2 and 3, 3. These are coming in the relation, so it is a reflexive relation. Other than it, all other elements can also come, but minimum requirement for the reflexive relation is the element related to itself must come in the set. Irreflexive relation. A relation R on set is called irreflexive if A, A does not belong to R for every element belongs to A. For the above example, if a relation is 1, 2, 2, 3, 1, 3, then it is a irreflexive because no self relation is coming in it. Like if in this 1, 1, 2, 2 or 3, 3 comes, then it will not be a irreflexive relation. Only the different relation pairs are coming in this. The next is symmetric relation. A relation R on set A is said to be symmetric if A is related to B, then B is related to A. For every A and B belongs to A, if A comma B belongs to R, then B comma B belongs to R. For example, If I'm defining the relation with 1, 1, 1, 2, 2, 1 on A 1, 2, 3, then it is a symmetric. We can easily see that if the 1, 2 is coming, then 2, 1 is also coming. Then it is a symmetric relation. Antisymmetric relation. A relation R on a set is said to be antisymmetric if for every A and B belongs to R. If A comma B related to R and B comma A related to R, then A is equals to B. For example, if a relation is 1, 1, 2, 1, 2, 3, on A is a set in which element 1, 2, 3 is coming, it is an antisymmetric relation. Then next is a asymmetric relation. A relation R on set is said to be asymmetric if for every A comma B belongs to A, if A comma B belongs to R, then B comma A should not belong to R. For example, if the relation is defined as 1, 2, 2, 3, 1, 3, it is a asymmetric relation. We can easily see if the 1, 2 is coming, then 2, 1 is not coming. If 2, 3 is coming, then 3, 2 is not coming. If 1, 3 is coming, then 3, 1 is not coming. So it is an asymmetric relation. Transitive relation. This is a normal transitive relation in the layman language. If A is related to B, then B is related to C, then A is related to C. A relation R on set is said to be transitive if A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. For example, the relation 1, 2, 2, 3, 1, 3 on A is a transitive relation. A relation R on set A is said to be equivalence relation if R is reflexive, symmetric, and transitive. That means for the relation to be equivalence, relations should satisfy the three conditions, that is reflexive, symmetric, and transitive. Two elements A and B that are related by a equivalence relation are called equivalent. Let A is equals to 1 to 3. The following relation on A are equivalent relation, that is 1, 1, 2, 2, 3, 3. And second is Cartesian product of A cross A, and third is 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 3, 1, and 3, 3. Equivalence relation, continuing, suppose we are having a set 1, 2, 3. The following relation on A are not equivalence relation. 1, 1, 2, 1, 2, 2, 3, 3, and that is a null set 1, 1, 1, 3, 2, 1, 3, 1. The references for today's lecture was textbook of Discrete Mathematics by Swapan Kumar Sarkar. Thank you so much for listening. If you like the video, then you can subscribe and like.